The objective of this course was to design and prototype a robotic platform inspired by nature, use this platform to develop a research hypothesis, and collect experimental data to validate our designs. Team Hopper was inspired by the pronking locomotion used by springboks in the wild. Springboks jump forward and upwards using a synchronized pushback of the front and hind legs. The reason for pronking is not entirely clear, but some scientists believe it is to dissuade predators from attacking as well as for recreational purposes. We were fascinated by the action and believe that this method of jumping locomotion will enable our robot to traverse rough terrain more efficiently as compared to purely wheeled locomotion. Our hypothesis is the implementation of a jumping mechanism on a wheeled robot reduces the cost of transport compared to traditional purely wheeled locomotion on incline, flat, and rough terrains. Hopper uses a dual spring jumping mechanism to achieve the desired pronking motion. We designed plungers mounted at both the front and rear of the vehicle, which use a combined strength of 4 compression springs to generate the desired jumping force. The chassis is made out of 2 acrylic sheets with standoffs and brackets to hold the jumping mechanisms and electronics. To absorb impact forces during landing, we selected compliant rubber wheels. A key component of our robot is a jumping mechanism. Here, a high-torque servo motor loads our rack-mounted plunger through a 284-to-1 gear train transmission. Our unique design allows our mechanism to both load and unload using just one motor. We achieve this through a negative groove in the loading gear, which demeshes with the loading gears once the plunger is fully loaded and allows the release of all the stored energy at once.
Initially, we planned for a larger jumping height. With this expectation, stability issues had to be considered, else the robot could land on its side or back, causing possible damage and ending trial runs prematurely. We decided to implement a reaction wheel that counteracts any rotational impulse caused by the jumping dynamics. For the final prototype, however, the planned jumping height was significantly reduced, resulting in little risk for the robot falling on its side or back. For this reason, the reaction wheel was not implemented on the final prototype.
The overall goal of our experiment was to determine our robot's cost of transport and compare its performance to other wheeled robots. The cost of transport is a dimensionless quantity which is calculated as the energy per unit mass per unit distance divided by the gravitational acceleration. It is a useful normalized metric to determine how efficient a robot is during locomotion. To determine the cost of transport, we measured the energy output of Hopper using a wattmeter, which measures the power consumed by the entire system. The energy consumed was derived from this data by taking power values at 2 discrete time points and multiplying them by the time step. The distance traveled was measured a few times on a flat and smooth surface. This chart shows the power consumption of the robot. A peak power draw of 4.6 watts can be observed. The energy consumption for the same trial shows a total consumption of 113.8 joules. The robot weighs in at 1034 grams. This data enabled the calculation of the cost of transport. Our measured data showed that the Hopper has a cost of transport of 80.92. Comparing this with purely wheeled rovers such as the Sojourner, which has a cost of transport of 122,000, and the Curiosity, which has a cost of transport of 10, it can be observed that the COT is measurably lower than the old rovers like the Sojourner, but pales in comparison to the modern rovers. It is also important to note that these rovers had many more complex subsystems, which contributed to an increased cost of transport. In possible future iterations where jumping distance and height is greatly increased, stability will have to be considered again. This could be achieved through our designed reaction wheel or through an alternative method of stabilization. We are also interested in increasing Hopper's maximum jump range and height. Possible mechanisms to achieve this could be solenoid-driven plungers or high-pressure and lightweight pneumatic actuators. Given the scope of the course and the allotted time, we feel proud of the system we were able to design. We had a lot of fun working as a team and picked up new skills along